Hello everybody, my name is eMoney SAD. Welcome back to my YouTube channel. Today we're going to go ahead and continue chapter 7. Today we're going to talk about E2 reactions. Elimination reactions, specifically E2, involves the use of a base. Specifically, the use of a strong base is required. Now, a strong base is an unstable base, which is what you want because you want it to be reactive. And then when you treat it with an alkyl halide, with a base, the alkyl halide can undergo a type of elimination process called a beta elimination. So here is the story of E2. Unlike SN2, which was a love story, the story of E2 is one of robbery. Now, in this E2 abduction, the strong base plans a robbery that will result in a 1-2 beta elimination. The strong base abducts the hydrogen from the beta position. The hydrogen never saw it coming. She didn't even have a chance to grab anything. She even leaves her electrons behind. That results in a double bond between the alpha and beta position of an alkyl halide. Now this double bond is the secret signal for the halogen to leave and meet at the rendezvous. The name for the secret plan is dehydrohalogenation because both the hydrogen and halogen are removed from the substrate. In short, a strong base abducts a hydrogen from the beta position of an alkyl halide and makes a run for it with the halogen leaving group. So, what are the blueprints for this abduction? Here we're going to take a look at the mechanism. Notice this reaction, just like SN2, happens all in one step, all in a concerted fashion, all right? So here's your alkyl halide, all right? Here's your alpha carbon because it's attached to a halogen. Here's your beta carbon because it's the carbon directly attached to the alpha carbon, all right? Here you have your strong and I guess smart base, all right, who starts this robbery off by abducting the hydrogen. All right, he abducts the hydrogen. The hydrogen bond, the electrons of the hydrogen bond here, gets dumped between the alpha and the beta carbon. Look at that. We form a double bond in between the alpha and the beta carbon. When that double bond forms, the leaving group leaves. All right. And then the base that has been protonated and your leaving group, they leave. What we have now is a carbon-carbon double bond. And again, this happens in a concerted fashion. All right. Now, what are the kinetics of this reaction? How do you determine the rate of the reaction? Well, the rate of the reaction is written as such, right? You have your rate constant, and it depends on the concentration of the alkyl halide and the base. So very similar to SN2, it depends on the concentration of two things, hence that 2 in E2. Now, we know the rate of the reaction is going to generally be found to be dependent on the concentration of both, and this observation is consistent with a second order process, hence the rate reaction. Now, this is the 2 in E2, like I said. All right. Now, you might ask, well, what is a strong base? Include who can carry out this robbery without getting caught by the cops? All right, fantastic question. Well, when you have a strong base that is a weak nucleophile, all right, you will always only get E2 reaction products, regardless of if your alpha carbon is primary, secondary, or tertiary. Now, what if you have a strong base that's a strong nucleophile? Well, then you're going to get a mix of products for primary and secondary alkyl halides and only E2 for tertiary. All right, so this is very important to know. Strong base, weak nucleophile. No matter how substituted your alpha carbon is, it will always only give you E2 products. All right, but if it's a strong base, strong nucleophile, for primary and secondary, you're going to get a blend of SN2. For primary, it's going to be more SN2 than E2. For secondary, it's going to be more E2 than SN2. And for tertiary, strictly E2. All right. So very important thing to keep in mind. Now, also notice in elimination reactions, in elimination reactions, we are forming products with double bonds. And we may need to compare the stability of these alkenes. So there's two things to remember here. All right. Your trans product is going to usually be more preferred than your cis product. All right. Having two big groups in a trans configuration maximizes the distance away from each other. That's really going to help in lowering the energy of your product because less steric effect. So trans is more stable than cis, and usually this trans product is preferred over the trans. The trans is more preferred than the cis. I'm so sorry. I'm getting my words jumbled up. Now, the more substituted your double bond is, the better, because those groups, the more groups, it's going to stabilize the double bond by delocalizing electron density. So think around the lines of electronic effect. Now, this is where E2 can potentially get a little confusing or hard to keep up with. All right. We can sometimes expect more than one E2 product for a single reaction. So in this discussion of all possible products we can obtain in an E2 reaction, there's going to be three terms we need to define to help our understanding. All right, the first term is regioselective. This is going to be your first step in any problem. How many unique beta positions are there and where are they? So here's an example problem. Here's your alkyl halide. How many beta positions does it have and where are they? Here's your alpha carbon directly attached to the halogen. Every other carbon attached to the alpha is a beta. So here's a beta position and here's a beta position. You have two unique beta positions. Now, in this regioselective step, if you have a beta position that has three hydrogens, if you have a beta position with three hydrogens, like this beta position right here, all right, you're just going to go ahead, not worry about anything, and just draw the product for that. So that means there's going to be a double bond right here, all right, and the halogen leaves. So that's your first product. Okay, you're going to identify how many different unique beta positions do you have. Here we have 1, 2. One of these positions has three hydrogens, this one right here. All right, that means there's nothing else in terms of stereoselectivity or stereospecificity that we're going to have to worry about. Nothing at all. We can just go about our elimination reaction and form that double bond right between the alpha and beta with the halogen leaving as a consequence of that. So here's our first product. Now, this is going to get more useful as we go through the steps, but you can identify your product. So after you draw all the products for E2, your most substituted product has a name, and that's your Zaitsev product. It's your most substituted product. Your least substituted product, all right, at the end of this is going to be called your Hofmann product. All right, now how do you know which is your major product? Is it your more substituted product or your least substituted product? That all depends on your base. If it's a bulky base, if it's a big base, then your Hofmann product is more favored. Here's examples of bulky bases. If it's not a bulky base, then your Zaitsev is preferred as your major product. Here are examples of not bulky bases. All right. Usually after you draw all your E2 products, all right, then you can begin to assign the most substituted product as Zaitsev, your least substituted product as Hofmann, and then looking at your base, you can determine what is your major product at the end. All right, now we covered the first step. How many different unique beta positions do we have? Here we have 2. All right, do any of them have 3 hydrogens? Yes, one of them does. All right, so for the 3 hydrogen beta position, just go and do your E2 reaction normally. That means you form a double bond between your alpha and beta, and of course, your leaving group leaves. All right, now we are going to look at each beta position separately for further steps. All right, like we said, if your beta position is a methyl group, right, it has 3 hydrogens, there's no extensive or complicated rules. Just deprotonate and go about. Now, when there is 2 hydrogens at a beta position, we need to stop and talk about stereospecificity. The products of this position, the products of the beta position with 2 hydrogens are going to give you a trans product and a cis product about the double bond that is formed. What is favored? Obviously, the trans. Fantastic. So here in our molecule, look, we have a beta position with 2 hydrogens. All right. That means when we form the double bond here, we're going to get the trans product, which looks like this, and we form the double bond between alpha and beta, and it can also look cis, like this. All right. So from beta positions with 2 hydrogens, you get the trans and the cis configuration. Remember, trans means if you cut the double bond in half, your 2 biggest groups are on opposite sides. That's why this product is trans. This one is cis because if you cut the double bond in half, your 2 biggest groups are on the same side. That is cis. And again, which product is favored? Usually trans predominates. Now, what if there's 1 hydrogen at a beta position? If that's the case, we need to talk about stereospecificity. Oh, I'm sorry. If there's 2 protons, you talk about stereoselectivity. If there's 1 hydrogen at the beta position, we talk about stereospecificity. To determine what the product looks like after that 1 hydrogen has been deprotonated, we're going to need to follow a few steps. All right, so here we have a different example, okay? All right, this molecule has 2 beta positions. We're only going to focus on this one. Why? Because this beta position has 1 hydrogen. So that means when our base comes along and steals the hydrogen, and this hydrogen dumps its electrons between the alpha and beta position, what does our product really look like? All right, this is going to require a few steps. What you want to do is you want to draw the alpha and beta position. Here's our alpha and here's our beta position, carbon, carbon like this. And then we're going to attach everything that's already there. So to this alpha position, we have a beta on a wedge, a bromine on a wedge. We drew that. We have our hydrogen here on a dash. We drew that. All right. And then we have this ethyl group and we draw that. Now at the beta position, let's erase this so we can see clearly. At the beta position, we have our phenyl group right there. We draw it. We have this methyl group right here. All right. We'll draw it. And then you have this hydrogen right here on a wedge. All right. So one note when you're drawing this is keep it consistent with the alpha position and beta position here. So if you're gonna draw your wedge here, all right, at the alpha position, draw your wedge down here for the beta position. If your dash is in the middle for that carbon for the alpha position, make it be in the middle for your beta position, and then your straight line, if it's at the bottom here in the alpha position, make sure it's at the top. All right, this is going to be useful for the next step after you've drawn everything. Now that you've drawn everything, your next step is to make sure that the hydrogen on one side and the halogen on the other side, on the alpha, all right, are across from each other on straight lines. So we need to get it to be anti-paraplanar. All right, that means we need the bromine to actually be on the straight dash, all right, not on the wedge, and we need our hydrogen to be on this straight dash, not on a wedge. What we can do, since we've drawn it this way, is we can switch this position right here and here. So now our bromine's on the straight line and the ethyl is on the straight line. But if we do that on one side, we're going to have to do it exactly symmetrical on the other side. So then we can switch our hydrogen and our phenyl group here exactly so. All right, and look how that's opposite. Notice how now our bromine and our hydrogen are across from each other on the plane, not on wedges or dashes. This makes it anti-paraplanar. Beautiful. Now our base is obviously going to come, steal the hydrogen. Hydrogen dumps its electrons here to form a double bond, and bromine leaves. So now we have this carbon-carbon double bond, but where on the double bond do we put our ethyl and hydrogen at the alpha And where do we put our methyl and phenyl group at our beta? Here's the hint. Everything on wedges, the ethyl and phenyl, have to go on the same side of each other because they're both on wedges. So at our alpha position, we'll draw our ethyl up, which means at the beta position, we have to draw our phenyl up because they're both on wedges. So they have to stay consistent. Now, everything on a dash has to also stay on the same side of the double bond. So our hydrogen and our methyl have to be on the same side of the double bond. We'll draw them at the bottom. All right, it could be the other way around. It'd be absolutely the same molecule if you did it the opposite way. All right, this is our product when there's only one hydrogen at the beta position. Okay, now an important thing to know. All right, an important thing to know is this is easier for cyclic reactants with beta positions with one hydrogen. All right, so if you have a cyclic compound, here's your alpha position. All right, it has a halogen. Here's a beta position with only one hydrogen. All right, it's way easier for cyclic compounds because this can only go through E2 if your halogen and your hydrogen at the beta position are on opposite wedge dash. Look, here it's opposite. Your halogen's on a wedge, your hydrogen's on a dash. Perfect. That means the reaction, the E2 reaction can happen, and instead you can form a double bond here. If they were both on wedges, you would not have a product that forms from that beta position. All right. Now, that's a lot of pieces to put together. All right. Now, if you have a reaction like this, oh my God, there's 3 beta positions. All right, that means we have to look at each beta position separately. Determine how many hydrogens are at each. All right, what base we're using, draw all the products, and then identify major and minor products. That is so much to keep track of. So let's put it all together. All right, let's put it all together and come up with a flow chart that's going to help us keep track of this. All right, here's a flow chart that I have created. All right, how to draw all the products for E2 reaction, and then at the end of it, determine major and minor products. All right, your first step is to locate the alpha carbon. We know how to do this. It's going to be attached to the halogen. Easy peasy. Then we want to determine how many and where our beta positions are. All right, that's also very easy. Where are our beta positions, unique beta positions? How many hydrogens are at each of those unique beta positions? All right. I'm sorry, how many unique beta carbons are there and where they are? Now that we've identified all our beta positions, we're going to look at one at a time and focus on that before we move on to the next beta position and draw the products for what happens with that beta position, okay? So you look at one at a time. How many hydrogens are at this beta position, right? So looking at our example here, all right, let's pretend we look at this beta position right here, all right? Then this one, all right? So at each beta position, stop. How many hydrogens are there, okay? If there is one hydrogen, okay, you have to think stereo specific. That means if it's acyclic, you need to get the hydrogen and the leaving group on opposite sides of the plane from each other. So anti-paraplanar, like what we just saw. And at the end of it, you're only gonna get one product from that beta position with one hydrogen. Now, if the compound is cyclic with one hydrogen, then you have to say, well, is my hydrogen and my leaving group on opposite wedge dashes? If the answer is yes, great. You can go and just do your beta elimination easy and you get one product. If they're not, you don't get any E2 products from that beta position. Okay, so that's an important thing to keep in mind. Now, you look at another beta position and you have 2 hydrogens. That means you want to think stereo selective. And regardless of cyclic or acyclic, well, actually, if it's acyclic, you get both cis and trans product where trans is preferred. But if it's cyclic, all right, you're only just going to draw a double bond there. You're not going to get both cyclic and acyclic because you can't be bending a ring structure like that. All right, so for cyclic, you'll get both cis and trans. For acyclic, you'll get both cis and trans. For cyclic, you have to be careful. Just draw a double bond there, and that is it. All right, now, if there's 3 hydrogens at a beta position, you're just dealing with a methyl group. There is nothing to keep track of here. You're just going to go and proceed with an elimination reaction. Easy peasy. All right, now, you've identified all your beta positions. You've said how many hydrogens are at each beta position. And you've done all the steps to draw all the products for every beta position. All right? Now, you want to identify your most substituted product. All right? That's going to be your most substituted product is going to be your Zaitsev product. Your least substituted product is going to be your Hofmann product. All right. Now, if you have a bulky base, your Hofmann product is going to be your major product. If you have a small base, your Zaitsev product is going to be your major product. All right. Now, with that, now that we understand this, now we know how to approach E2 products and drawing all of them. Let's just go ahead and do practice problem after practice problem, all right? Starting off with the one that we just saw before we did our flowchart. Now we can apply our flowchart to this specific problem. First step, all right, we're going to do this step by step. All right, you want to find your alpha carbon. Here is our alpha carbon. It's attached to the chlorine. Beautiful. All right, so that's our alpha carbon. Now we want to identify all our beta positions. All right, these are all the carbons attached to the alpha carbon. Here's a beta carbon. Here's a beta carbon. And here is a beta carbon. We're going to go ahead. We're going to number these. Actually, we're going to label these A, B, and C. All right, so we've identified our alpha carbon, check. We've identified our beta positions, check. How many are there? There are 3 beta positions. All right, you want to write all this information as you go so you don't get too confused. Okay, now we're going to look at every beta position alone. We're going to look at our A beta position. How many hydrogens does this beta position have? It's just a methyl. It has 3 hydrogens. We know exactly what to do when there's 3 hydrogens. We do not worry about stereoselective or stereospecific. We just do our good old elimination reaction and form a double bond between the alpha and beta position. All right. So that means everything else stays the same. We don't change any of this. Our base is going to come in, steal a hydrogen. Hydrogen is going to dump its electrons between the beta and alpha position, and then your chlorine will leave. So what you form is just a double bond right here. This is our first product. All right, is very important. All right, that's our first product. Beautiful. Now we're going to go ahead and look at position B. All right, that's a beta position. How many hydrogens does it have? 2 hydrogens. Now, you might be thinking, oh, 2 hydrogens. We're going to need a cis and a trans product. All right? Hold your horses, though. This is a cyclic molecule. All right? It's a ring. We're not going to get both cis and trans. We're simply going to form a double bond between the beta and alpha position, and that's that. All right? So what that means is our base is going to come, steal a hydrogen from this beta position. The hydrogen is going to form a double bond between the alpha and the beta, and then our leaving group leaves. So what that means is our product for this beta position is going to look something like this. And that's it. Because it's cyclic, we only get 1 product, so not 2, not a cis and trans, all right? So this is our second E2 product. Now we can look at position C. All right, that beta position has 1 hydrogen. All right, this is very important. It only has one hydrogen. All right, so let's look at this hydrogen. All right, you have an ethyl group on a dash, and our hydrogen here hiding is on a wedge. All right, now let's look at our flow chart. We have one hydrogen, so we're thinking stereospecific. Is it acyclic or cyclic? We are dealing with a cyclic compound, obviously. Look at that, that's a ring structure. Now, the question you ask yourself afterwards is, well, is the hydrogen and the halogen on opposite wedge dashes? Well, let's look. Chlorine is on a wedge. Hydrogen is on a wedge. They're both on wedges. They're not on opposite. No, they're both on wedges. That means no product is going to occur here. We actually cannot have a E2 reaction that happens at this position. We get no products from this beta position. That means we get a total of 2 products for this reaction. Now, don't get carried away. We're not done yet. We have to look at the double bond we formed and say how substituted this is. All right, this double bond is di-substituted. It has one group here and another group here. All right, this double bond has 2 total groups. All right, that means it's di-substituted. Beautiful. This double bond here, though, it has 1 group right here, 2 right here, and then 3 right here. This product has 3 total groups on the double bond. It's tri-substituted. Fantastic. Which one is our major product? Well, our major product depends on the base. All right, our base is just a hydride. This is a small base, not a bulky base, small baby base. All right, that means our major product is the Zaitsev product. What is the Zaitsev product? I cannot spell that. Let me try that again. Small base means our major product is the Zaitsev product. The Zaitsev product is your most substituted product. So, which one is our most substituted product? Product number 2. This is our Zaitsev product, and it's our major product. Why? Again, because of the base. Our base is not bulky. It's a small base. So it's going to prefer the more substituted product. Now, if it was a bulky base, it would be the opposite. Our least substituted product would be our major product. All right, so that's how you approach these kinds of problems. All right, let's do another practice problem here. All right, let's try to solve this one. Okay, this problem, we have our starting material, and we have this base right here, DBU. Fantastic. First step, all right, first step as always, identify your alpha carbon. Here's our alpha carbon. Beautiful. Second step, find your beta positions. All right, find them, and then how many do you have? Okay, so we're going to look at here. Where are our beta positions? Well, we have a beta position here, and we have a beta position here. We have 2 beta positions. Fantastic. We're going to label one A, and we're going to label one B. All right, so then step 3 is to look at each beta position. So we're going to look at beta position A. All right, how many hydrogens? How many hydrogens? All right, so let's look at that beta position right here. How many hydrogens is there? It's bonded to this carbon right here. All right, double bonded over here and single bonded here. There are 4 things attached to that beta position, and there are no hydrogens here. So we really can't do an elimination reaction at that beta position. Cool, that makes it easier for us. What about the beta position B? How many hydrogens are there? All right, let's look at it. Let's take a good look right here. All right, at this beta position, there is just 1 hydrogen. All right, fantastic. There is 1 hydrogen. All right, you know what that means? All right, 1 available hydrogen means we need to think stereo specific. All right, we need to think stereo specific. All right, so that takes us to step 4. We're gonna work with with the only beta position we have. All right, we're thinking stereospecific, which means we're gonna have to draw the alpha carbon and the beta carbon here. All right, we're gonna draw them right here. Boom. All right, and we're gonna label them alpha and beta. And now we're gonna attach everything on the alpha, and then we're gonna attach everything on the beta. Now, if you look at the alpha, you have this phenyl group, so we're just gonna do that. Phenyl. All right, then we have on this dash a hydrogen. We're gonna keep our dashes in the middle, hydrogen right here. And then on the wedge we have iodine. Beautiful. All right, now we wanna look at our beta carbon. All right, here's our beta carbon right here. What's attached there? All right, well, what's attached there is we have on the wedge, just a methyl group. Then on a dash, we have a hydrogen. Look at how we put the wedges across each other opposite, and how the dashes are also across each other right in the middle. And then on this just straight line, all right, right opposite from the other straight line is just a methyl group. And we're just gonna write methyls here. All right, beautiful. Well, now what we want to do, all right, what we want to do is we want to get this halogen at this position here. All right, so we're going to switch these two. Now, if we switch these two, all right, what we're going to have to do is also switch these two right here. This methyl, oh, that didn't write, right? All right, we're going to switch this methyl with the hydrogen, actually. All right, so we're switching the phenyl and halogen on this side. Perfect. All right, and then we're going to switch the methyl and hydrogen here. All right, it's going to be okay. So let's draw what that looks like. Ooh, I need space. So what we're going to do is we're going to erase some stuff here. All right, so on one side, we'll switch these two. All right, and then on the other side, we're going to switch just the methyl and hydrogen. Why? Because on the straight lines, we want our halogen and we want our hydrogen. And when we do that, then this phenyl group goes on the wedge. Hydrogen stays as is, no problem. All right, and then if our hydrogen here is on the dash, then we're going to have one methyl on the dash and one methyl on the wedge. And perfect. Look how our hydrogen and halogen are anti-paraplanar. Okay, they're right across from each other. That means that our base can come in, steal a hydrogen, hydrogen dumps its electrons to form a double bond here, and the iodide leaves. Okay, so now let's draw our final product, what that's going to look like. All right, we have a carbon-carbon double bond. Okay, we want to draw everything on wedges on the same side of the double bond. That means we're going to write our phenyl up and we're going to write our methyl up because they're both on wedges. And then everything on dashes we're going to draw on the same side of the double bond. So here our methyl, let's do it in a different color so we can be able to identify. We'll draw our methyl down here and we'll draw our hydrogen here. And this is our final and only product for this E2 reaction. All right, now let's do one more, and then I'm going to leave 2 for you to attempt. And I want you to post what you get in the comment section below, and we can talk about it. All right, so this is the last one we're going to do. All right, we're going to identify our alpha position. We're going to identify all our beta positions. All right, this beta position has no hydrogen, so we're not going to worry about it. This beta position has 1 hydrogen. All right, so we have 1 hydrogen here. We need to think specific, yes. All right, but it's cyclic. So what that means is we want to make sure is our halogen and our hydrogen on opposite wedge dash. Are they? That's the question we need to ask. So let's see. Our halogen, our chlorine is on a wedge. Our hydrogen is on a dash. They're opposites of each other. Yes, fantastic. That means we get one product. One product where our base is going to come steal the hydrogen. Hydrogen's going to dump its electrons between the alpha and beta position. All right. And then the halogen leaves. So what that means is our product is going to look something like this. There's a double bond here. Halogen is gone. All right, and we keep all our substituents here. This is our one and only product for SN2 and E2. Fantastic. I'm going to leave this problem and this problem for you to do. Next session is going to be us. Maybe we can review those two, and then we're going to do even more combined SN2 and E2 problems before we go into E2, E1, and SN1. So stay tuned. Let me know if you have any questions. Good luck, happy studying, and have a great